Consider series A and series B with positive terms, such that each term in A sub k is greater than or equal to its corresponding term in B sub k. K is greater than or equal to 1 for this example. What conclusion could we make about B if we know A converges? B also converges. Because A converges, it has a finite area, and the terms in B are smaller than the terms in A. What conclusion could we make about A if we know B diverges? A also diverges, because the terms in A are larger than the terms in B, so if B does not have a finite area, neither will A. Here is our theorem for the comparison test, also known as direct comparison test, since we'll also be learning about the limit comparison test. When should we use the direct comparison test? We should use this when the series resembles a p-series or when the series resembles a geometric series. Informally speaking, if the larger series converges, then the smaller series must also converge. If the smaller series diverges, then the larger series must also diverge. Let's try some examples. When I choose a series to compare to, first of all, I need to know if that comparison series converges or diverges. And then I have to establish that it is less than or greater than, depending on what I'm going for. I don't know for sure if this converges or diverges, but I do know a similar looking series. So does this geometric series converge or diverge? Absolute value of r is, yes, indeed, less than 1. Therefore, this is a convergent geometric series. Our original series will converge if each term of this series is less than or equal to each term of this series. Because this has a bigger denominator than this one, it is a smaller fraction, so this is a true statement. Since this is a true statement, and the larger series converges, the original series will also converge by direct comparison test. You could also use DCT to represent direct comparison test. To compare, I want to find a series that looks kind of like this one. The series to me that looks kind of like this one is 1 over n, the harmonic series, which we already know diverges. So the only way comparing to the harmonic series will help me is if the harmonic series is less than or equal to the original series. Here we have a smaller denominator, which does indicate a larger fraction. So this is a true statement. And knowing that our smaller series diverges, we can conclude that our original series will also diverge. Now for number 3, I think it would be tempting to want to compare to 1 over root n. But what would that look like? Well, we know the left fraction is less than or equal to the right side fraction because this denominator is bigger than this one. But we also know this diverges by the p-series test. So is it helpful to compare to a larger divergent series? No, it's not. What if we compare this to 1 over n plus 1? What would be my inequality? Because this has a smaller denominator, it will be a larger fraction. This comparison is only helpful if this series diverges. If this series converges, then that doesn't tell us anything. But how do we determine if 1 over n plus 1 diverges or converges? I would use the integral test. Yeah, this is going to diverge by the integral test. So, is this a helpful comparison? Yes, because the smaller series diverges, which means the larger series will also diverge by direct comparison test. If you feel uncomfortable with using the direct comparison test, you can pretty much go without using it. The reason why we talk about the direct comparison test is that it can make for really efficient determination of convergence or divergence. But that's only if you're comfortable with basic series and comfortable with using that test. Pretty much any time you use the direct comparison test, you could have used the limit comparison test instead. The limit comparison test says that if a sub n and b sub n are both greater than 0, and the limit of a sub n over b sub n exists, has a limit, is finite and positive, then both the series will converge or they both diverge. This conclusion is similar to the integral test, where the behavior of one is the same as the behavior of the other. So if the comparison series converges, the original will also converge. And if the comparison series diverges, the original will also diverge. That helps you avoid figuring out if one is larger than the other or not. This limit comparison works well when comparing a messy algebraic series to an easier p-series. To choose the p-series, disregard all but the highest powers of n in the numerator and denominator. Let's use it. The series I'm going to compare to is the p-series 1 over n squared. Is that a convergent or a divergent p-series? This series converges by the p-series test. Our original is a sub n, and our comparison is b sub n. Keep in mind that a sub n divided by b sub n is just a sub n times 1 over b sub n. That helps because we usually have complex fractions, and so this just saves us some space while we're writing. When taking the limit as n approaches infinity, we only consider terms of highest degree. And our result is 1/3. What does that mean? We used the limit comparison test. 1/3 is finite and positive. If that is true, then the behavior of the sum of a sub n and the sum of b sub n is the same. Therefore, our original series converges by limit comparison test. To help you figure out what you want to use for b sub n, you can consider the highest degrees of the numerator and the denominator in a sub n and reduce those to get a similar p-series to compare to. This makes b sub n 1 over root n. 1 over root n is a p-series. Does it converge or does it diverge? This diverges because p is 1/2, which is not greater than 1. So let's try limit comparison test. One is finite and positive. Therefore, both series will have the same behavior, which means the original series diverges by limit comparison test. For number 6, a sub n. For number 6, we have a sub n. To get b sub n, we consider the terms of highest degree, and to make it even simpler, we're going to use 1 as the coefficient for each. B sub n is 1 over n squared, and 1 over n squared converges by the p-series test. Because p, which is 2, is greater than 1. Let's evaluate the limit now. And we have a finite and positive result. Therefore, our series will have the same behavior. So if the comparison series converges by PST, then the original series will also converge by limit comparison test.